The maximum current is produced in the stator windings is 2. The zero position of the rotor is used as a reference for determining the rotor angular position, whereas the output of the transmitter is given to stator winding of the control transformer, which is shown in the figure. Okay, the current of the same and magnitude flow through the transmitter and control transformer of the synchronous. Because of the circulating current, the flux is established between the air gap flux of the control transformer. So when you are saying about the flux axis, actually the flux axis of the control transformer and the transmitter is aligned in the same position, whereas the voltage generated by the rotor of control transformer is equal to the cosine of the angle between the rotors of the transmitter and the controller. The voltage is given as E of t is equivalent to k dash of VR cos of phi sine omega ct, where phi stands for an angular displacement between the rotor axis of transmitter and controller, whereas the phi is equivalent to 90 degree. The axis between the rotor of transmitter and control transformer is perpendicular to each other, whereas the figure shows the zero position of the rotor of the transmitter and the receiver. So we have to consider the position of the rotor and transmitter is changing in the same direction. When you are considering an angle theta r, which deflects the rotor of the transmitter, and thereof the control transformer is kept theta c. The total angular separation between the rotor is given as an phi is equivalent to 90 degree minus theta r plus theta c. Whereas the case of a rotor terminal voltage of synchro transformer is given as E of t is equivalent to k dash of VR. So we'll have a cos of 90 degree minus theta of sine value. So cos of 90 minus theta is equivalent to sine theta. So sine theta r minus theta c of sine of omega ct. Whereas the small angular displacement between the rotor position is given as sine of theta r minus theta c is equivalent to theta r minus theta c. So on substituting the value of angular displacement, we get what we're getting of Abdina. We'll be getting of an E of t is equivalent to. So this is about our positional control system. So we'll have a synchro control transmitter, synchro control transformer, and we'll have around an AC amplification. Okay, so this is the wave, that is the synchro transmitter, and the control transformer together, which is used for detecting the error over on it. The voltage equation shown above is equal to the shaft position of the rotors of the control transformer and transmitter. So whenever we are considering the error signal, which is applied to the differential amplifier, which gives input to the servo motor. The gear of the servo motor rotates the rotor of the control transformer. Okay, so this is the error signal which is applied over on it. So the output of synchroreactor, which is a modulated signal, the modulating wave, which above shown the misalignment between the rotor position and the carrier wave, where Ks is the error vector, where E of t is equivalent to theta r minus theta c. So this is about an synchron. So when we are saying about an microsyn, actually one version of RBDT which is called as an microsyn, it is to be a variable reluctance transducer. Okay, for the connection of exciting windings, so that we have an instantaneous pole position for the current directions which are shown over here. Actually, it is most widely used in sensitive gyroscopic instruments. So at null position, voltage induced in coils 1 and 3, which is balanced by those of 2 and 4. By the motion of input shaft from null position, which increases resistance of 1 and 3, and will have a decreases to that of 2 and 4. So when you are saying about that, actually in the arrangement, the coils are connected in such a way that the null position of the rotary element, the voltages induced in coils 1 and 3, which are balanced by voltages induced in coils 2 and 4. The motion of rotor in the clockwise direction increases the reluctance of coils 1 and 3, while decreasing the reluctance of coil 2 and 4. So thus giving a net output voltage E naught. The movement in the counterclockwise direction causes a similar effect in coils 2 and 4 with a 180-degree phase shift. A direction sensitive output which can be obtained by using phase sensitive demodulators. So as explained in the LVDT section already. So when you are saying about a microsyn transducer, they are used extensively in applications involving gyroscope. By the use of microsons, the very small portions can be detected, giving output signals as low as 0.01% of changes in angles. The sensitivity of the device, which can be made as high as 5 volt per degree of rotation. The non-linearity may vary from 0.5% to 1% of full scale. The main advantage of these transducer is that the rotor does not have windings and slip rings. Similarly, the magnetic reaction torque is also negligible. So when we are concluding that, what are the advantages and disadvantages? Actually, Advantages of microsyn, it is to be simplicity of design, will have a lower parse count and space savings. It has a low noise, it will have a fast transient response, and it will have a low cost. Whereas in the case of an disadvantage, actually the low efficiency, if the input and output difference is large and they have a significant heat dissipation, it may require a heat sink, and apart from that, it is have a capable exclusive of step down operations. So by that, so we'll be seeing about an the next class. So thank you all.